So let's look at the new instructions and their specification for hardware transactional memory in the Power architecture. And they were introduced in 2013, and when we have seen that, we will later in the lecture see how Power 8 support these instructions. I mean, some parameters about various things. Okay, first of all, every memory access is either transactional or non-transactional, and it's transactional if it appears between a begin and end pair. That means all existing codes there without begin and end, I mean before introducing this, they are all non-transactional as expected. Okay, so first one little remark, and there is a dot at the end of each instruction here. A dot means that it sets, the instruction sets a condition code so that the program can do a conditional branch on the result. So all these instructions write some kind of result, whether it succeeded or not. Just as a compare instruction does, and then the results are written to a 4-bit register CR0. There are 8 of these registers. And so some instructions set this field. This is for integer registers, I mean for writing the result about integer comparisons, and CR1 is for floating point. But some instructions can specify explicitly exactly which such a group of 4 bits should be modified. Okay, but I will not talk about that anymore. So the first two start and end a transaction. This is the intended by the software to commit the transaction that it has reached the end. If it wants to give up, it can do a transaction abort. Okay, and then there are two interesting instructions, transaction suspend and transaction resume. And, well, they leave and return to the most recent transaction. We will see later why they can be useful. These two we will not talk about because we don't have to consider them when writing application code. So there is a bit called the transaction doomed, and it's set to 0 as expected at the beginning and at the 1 at the failure. Okay, so at the beginning most registers are saved automatically at this tBegin, but not this one, since it will contain the result of the instruction. Okay, so I mean the tBegin should not save the old value. Instead, it will write a value into this one, and the tEnd should not restore the previous value. Instead, it will write the result to CR0. Okay, and if there is a transaction failure, an error handler will be executed. And it can be failed due to conflict with another transaction, as just explained. I mean, not just, but as explained during this lecture. Or it can fail by itself. And this is called self-induced failure. And one is to execute the abort. Another is to exceeding some hardware limitations. How many nested transactions are allowed, or how much data is allowed to be written, or which instructions are not permitted. What they do we can ignore, but well, this is to enter a low energy mode, and this is data cache block invalidate. Okay, so it's sufficient to know that there are some instructions that are not very useful and even forbidden within a transaction. Okay, so if it fails, this failure handler should either try this transaction again or do something else. For the lab, when we use the GNU transaction atomic, we don't have to write error handler to do the operation with locks, but it will just rerun the transaction. Okay. Also interesting to note, there is no guarantee that there is fairness or progress, I mean by the hardware. So that should be handled by the application programmer in some sense. Realistically, if the transactions are too big and they just retry all the time, then there will be no progress, obviously. So they should be written in a more clever way. Okay, transactions, they can be nested, and when we come to transaction end, there are two options: either to end the most recent transaction or to end most of them. But a failure terminates all transactions.